Starship. Starship is a two-stage to-orbit, TSTO, or two-stage, fully reusable, super heavy-lift launch vehicle, SHLLV, under development by American aerospace company Space Exploration Technologies Corp., more commonly known as SpaceX. Currently built and launched from SpaceX Starbase, previously known as SpaceX South Texas Launch Site and SpaceX Private Launch Site, in Texas, USA, Starship is intended as the successor to the company's Falcon 9, a partially reusable, two-stage to-orbit, medium-lift launch vehicle (MLV), and Falcon Heavy (FH), a super heavy-lift launch vehicle with partial reusability, rockets, and is part of SpaceX's broader reusable launch system development program. If completed as designed, Starship would be the first fully reusable orbital rocket and have the highest payload capacity of any launch vehicle to date. As of March 2026, Starship has launched 11 times, with 6 successful flights and 5 failures. The vehicle consists of 2 stages, the Super Heavy booster and the Starship spacecraft, both powered by Raptor engines burning liquid methane, CH4, the main component of natural gas, also gas, methane gas or fossil gas, and liquid oxygen, sometimes it is abbreviated as LOX or LOXygen. Both stages are intended to return to the launch site and land vertically at the launch tower for potential reuse. Once in space, the Starship upper stage is intended to function as a standalone spacecraft capable of carrying crew and cargo. Missions beyond low Earth orbit, LEO, would require multiple in-orbit refueling flights. At the end of its mission, Starship re-enters the atmosphere using heat shield tiles similar to those of the Space Shuttle or Space Transportation System, STS. SpaceX states that its goal is to reduce launch costs by both reusing and mass-producing both stages. SpaceX has proposed a wide range of missions for Starship, such as deploying large satellites, space station modules, and space telescopes. A crewed variant, developed under contract with the National Aeronautics and Space Administration, NASA, is called the Starship Human Landing System, Starship HLS. A lunar lander variant of the Starship spacecraft, which is scheduled to transfer astronauts from a lunar orbit to the surface of the Moon and back as part of the Artemis program, beginning with Artemis 3 currently scheduled for 2027. SpaceX has also expressed ambitions to use Starship for crewed missions to Mars, SpaceX Mars Colonization Program, also referred to as Occupy Mars. SpaceX began developing concepts for a super heavy-lift reusable launch vehicle as early as 2005, with different names throughout the years. Starship's current design and name were introduced in 2018. Development has followed an iterative and incremental approach, involving a high number of test flights and prototype vehicles. The first launch of a full Starship vehicle occurred on April 20, 2023, and ended with the explosion of the rocket 4 minutes after liftoff. The program has failed to meet many of its optimistic schedule goals, with its development having hit several setbacks, including the failure of the first 4 Starship Block II upper stages in 2025. When stacked and fully fueled, Starship has a mass of approximately 5,300,000 kilograms, 11,700,000 pounds, a diameter of 9 meters, 30 feet, and a height of 121.3 meters, 398 feet. The rocket has been designed with the goal of being fully reusable to reduce launch costs. It consists of the Super Heavy booster and the Starship upper stage, which are powered by Raptor and Raptor vacuum engines. The bodies of both rocket stages are made from stainless steel and are manufactured by stacking and welding stainless steel cylinders. These cylinders have a height of 1.83 meters, 6 feet, and a thickness of 3.97 millimeters, 0.156 inches. Domes inside the spacecraft separate the methane and oxygen tanks. SpaceX has stated that Starship, in its baseline reusable design, will have a payload capacity of 100,000 to 150,000 kilograms, 220,000 to 331,000 pounds, to low Earth orbit and 27,000 kilograms, 60,000 pounds, to geostationary transfer orbit, GTO. Super Heavy was initially 71 meters, 233 feet, tall, in its Block 1 and Block 2 design, now retired, while Block 3 Super Heavy is 72.3 meters, 237 feet, tall. Super Heavy is 9 meters, 30 feet, wide, and is composed of 4 general sections, in ascending order: the engines, the oxygen tank, the fuel tank, and the interstage. The 2 cryogenic propellant tanks on Super Heavy are separated by a common bulkhead, a similar structural design to the S2 and S4B stages on the Saturn V, a retired American super heavy-lift launch vehicle developed by NASA under the Apollo program for human exploration of the Moon. After Starship's second flight test, the common dome's design was changed to be more elliptical, altering the propellant capacity of both tanks by a small amount. Each fuel tank possesses roughly 74 stringers for structural reinforcement, attached to their interior walls. The booster's 2 tanks hold a combined 3,400,000 kilograms, 7,500,000 pounds, of propellant, 2,700,000 kilograms, 6 million pounds, of liquid oxygen and 700,000 kilograms, 1,500,000 pounds, of liquid methane. With a mixture ratio of 3.6 parts oxygen to 1 part methane, 78.3% of propellant is of liquid oxygen. Fuel is fed to the engines via a single liquid funnel, and channeled into distribution manifolds of the engines. This fuel system was upgraded on Block 3 boosters, featuring a substantially larger transfer tube connecting the engines and the methane tank. Block 1 and Block 2 boosters both have a single booster quick disconnect, along with multiple quick disconnects for the outer engines, while Block 3 boosters have 2 quick disconnects. One disconnect feeds liquid oxygen into the vehicle, the other feeds liquid methane. The oxygen tank ends at the thrust structure of the vehicle. While the outer 20 engines are mounted to the walls of the aft bay, the inner 13 are mounted onto the thrust puck, a part of the aft dome. Large steel structures are attached to the bottom of the dome, reinforcing the puck sufficiently to fully support the inner 13 engines, and at the same time providing pathways for methane and oxygen into the engines. In addition, large filters were added in this region beginning on booster number 10. Liquid oxygen is supplied by a header tank during landing burn for the inner 13 engines. On booster number 15, the header tank had at least 9 additional tanks attached, increasing capacity for the landing burn. The added tanks may have been present on boosters numbers 12, 13, and 14, though this was unconfirmed as of February 2025. Booster number 5 was the only 29-engine booster to receive a header tank, mounted to the side of the oxygen tank instead of being integrated with the thrust puck. The methane funnel is partially contained within the header tank, as the methane sump is directly below it. On booster number 7 and all subsequent vehicles, 4 aerodynamic chins are located on the outside of the oxygen tank, providing aerodynamic lift during descent, as well as housing batteries, composite overwrapped pressure vessels, COPs, for spin start, and CO2 tanks for a vehicle fire suppression system. Earlier on vehicles with hydraulic power units, HPUs, COPs dedicated to engine ignition, batteries, and communication antennae were located within the HPU cover instead of the chins. Super Heavy is powered by 33 Raptor engines, which on Block 1 and Block 2 vehicles are housed within a dedicated shielding compartment. This compartment is not present before engine installation, thus, boosters are roughly 3 meters shorter prior to engine installation. The outer 20 engines, arranged in a ring, are fixed in place. To save weight, the 20 engines are started using ground support equipment on the launch mount and cannot be reignited for subsequent burns. The inner 13 engines are equipped with gimbal actuators and reignite for the boost back and landing burns. After Starship's first flight test, this gimbaling system was switched from a hydraulic system to an electric one, enabling the removal of the hydraulic power units. This change was made to the upper stage after the second flight test. During the ascent and boost back burns, the engines draw propellant from the main tanks, with the liquid oxygen being drawn from a dedicated header tank during the landing burn. Like the thrust vector control system, the engine shielding, which isolates individual engines in the event of a failure, was upgraded after Starship's first flight test, alongside the fire suppression system. The aft bay has 18 vents visible on the outside of the booster, which are believed to be connected to the outer 20 engines, while the center engines vent directly below the launch pad. The Raptor engine uses a full-flow staged combustion (FFSC) cycle with oxygen and methane-rich turbopumps. Before 2014, only 2 full-flow staged combustion rocket engine designs had advanced enough to undergo testing: the Soviet RD-270 engine project in the 1960s and the Aerojet Rocketdyne Integrated Powerhead Demonstrator (IPD) in the mid-2000s. To improve performance, the engines burn subcooled propellant. In other words, the propellants are cooled below their respective boiling points to further increase their density and the engine mass flow rates. The Block 1 version of the booster, used through November 2024, produced a total of 73.5 meganewtons, 16,500,000 pounds force, just over twice that of the NASA Saturn V first stage, S1C, with this total being expected to increase to 80.8 meganewtons, 18,200,000 pounds force, for Block 3 boosters and later up to 98.1 meganewtons, 22,100,000 pounds force, with the Block 4 vehicle. The 33 Raptor engines collectively produce large shock diamonds in the exhaust jet, visible during ascent and descent. During unpowered flight in the upper atmosphere, control authority is provided by cold gas thrusters fed with residual ullage gas. 4 perpendicular vents are located within the interstage. Additional vents are located just below the common dome, pointing down toward the engines at a slight angle. The Block 3 booster contains an updated aft dome, with metallic heat shield tiles mounted upon it. The interstage is equipped with 4 electrically actuated grid fins made of stainless steel, each with a mass of roughly 3,000 kilograms, 6,600 pounds. The fins remain extended during ascent to save weight, though this results in mild warping during stage separation. The interstage also has protruding hardpoints, located between grid fins, allowing the booster to be lifted or caught by the launch tower, nicknamed Mechazilla. The ability to lift a booster from these hardpoints was proven on August 23, 2022, when Booster 7 was lifted onto the Orbital Launch Mount A, OLMA. The first catch of a booster occurred on October 13, 2024, using Booster 12. After the first Starship test flight, all boosters have an additional 1.83 meters, 6 feet, tall vented interstage to enable hot staging. During hot staging, Super Heavy shuts down all but the 3 center engines, while the second stage fires its engines before separating, thus the second stage pushes off from the first stage, giving added thrust. The vented interstage contains a dome to shield the top of Super Heavy from the second stage's exhaust. Elon Musk in 2023 claimed that this change might result in a 10% increase in the payload to low Earth orbit. Beginning with Booster 11, the vented interstage is jettisoned after completion of the boost back burn, to reduce mass during descent. As of December 2025, SpaceX does not intend to jettison the interstage when flying Block 3 boosters, as the vented section will be directly integrated into the vehicle. On Block 3 boosters, the interstage is directly integrated into the methane tank, and the number of grid fins is reduced from 4 to 3, in a 90-90-180 degree arrangement. These grid fins are roughly 1.5 times the size of the Block 1 and Block 2 grid fins, and are positioned lower on the vehicle. According to SpaceX, the repositioning reduces the heat experienced during stage separation. Additionally, the fins are integrated with the catch pins. The Block 2 version of Starship is 52.1 meters, 171 feet, tall, 9 meters, 30 feet, wide, and is composed of 4 general sections: the engine bay, the oxygen tank, the fuel tank, and the payload bay. The retired Block 1 was constructed in a similar manner, though it was only 50.3 meters, 165 feet, tall. Elon Musk stated in 2021 that the vehicle has a dry mass of roughly 100,000 kilograms, 220,000 pounds. The windward side is protected by a heat shield, which is composed of 18,000 hexagonal black tiles that can withstand temperatures of 1,400 degrees Celsius, 2,600 degrees Fahrenheit. It is designed to protect the vehicle during atmospheric entry and to be used multiple times with minimal maintenance between flights. The silica-based tiles are attached to Starship with pins, and had small gaps in between to allow for heat expansion. After Flight Test 4, SpaceX added a secondary ablative layer under the primary heat shield, though this was only added to the flaps of the Flight Test 6 vehicle. This ablative layer is likely composed of pyrin, which is similar in composition to carbon composites. The total mass of the heat shield and ablative layer of a Block 1 ship is 10,500 kilograms, 23,000 pounds. After Flight Test 10, SpaceX added a felt, called crunch wrap, between the gaps in between the tiles to prevent heat seeping in. The propellant tanks on Starship are separated by a common bulkhead, similar to the ones used on the S2 and S4B stages on the Saturn V Super Heavy Lift launch vehicle. While Block 2 vehicles use an elliptical dome, the common and forward domes of the Block 1 design were more conical. Block 1 vehicles only had 24 stringers within the oxygen tank, while Block 2 vehicles had these added to the methane tanks. The vehicle's tanks hold 1,500,000 kilograms, 3,300,000 pounds, of propellant, consisting of 1,170,000 kilograms, 2,580,000 pounds, of liquid oxygen, 78%, and 330,000 kilograms, 730,000 pounds, of liquid methane. Fuel is fed to the engines via 4 downcomers, with 3 smaller downcomers feeding the vacuum raptors, RVACs, and the central downcomer feeding the inner 3 engines. The central downcomer connects to a large sump, instead of directly to the methane tank itself. The original design only featured a single downcomer. The liquid oxygen downcomer extends into the liquid oxygen tank, with a small expanded portion of unknown purpose. 2 additional downcomers route methane and oxygen from the header tanks. A camera is located on the walls of the tank, pointed towards the payload bay. The oxygen tank terminates with the thrust structure of the vehicle. The RVACs are mounted directly to the aft dome, which has reinforcements mounted inside of the tank. The 3 sea-level engines are mounted on the thrust puck, which forms the bottom of the aft dome. A conical steel structure is mounted inside the bottom of the dome, reinforcing the thrust puck enough to enable its support of the inner 3 engines. The propellant lines on the vehicles are all vacuum jacketed, reducing boil-off while in orbit. Starship is powered by 6 Raptor engines, which are housed within a dedicated shielding compartment. Blocks 1 through 3 feature 3 sea-level engines, as well as 3 engines optimized for operation in the vacuum of space, called RVACs. Block 4 ships are expected to feature 3 additional RVACs. The sea-level engines are equipped with gimbal actuators, and reignite for the landing burns. After Starship's second flight test, this gimbaling system was switched from a hydraulic system to an electric one, enabling the removal of the hydraulic power units. This change was made to the booster after the first flight test. There are 4 engine chill lines on board the vehicle, though 2 of these lines may serve another purpose. Each engine is protected by a dedicated shielding compartment. Beginning with S-25, the Block 1 design had between 14 and 16 such vents. Additional vents were added after Flight 7. The fire suppression system, which uses gaseous nitrogen to purge the engine bay during flight, was upgraded after Flight 7. A similar system on the booster uses carbon dioxide to purge the individual engine compartments during flight and static fires. The Raptor engine uses a full-flow staged combustion cycle, which has both oxygen and methane-rich turbopumps. Before 2014, only 2 full-flow staged combustion rocket engine designs had advanced enough to undergo testing, the Soviet RD-270 project in the 1960s and the Aerojet Rocketdyne integrated powerhead demonstrator in the mid-2000s. To improve performance, the engines burned supercooled propellant. The Block 1, first version of the ship, used through November 2024, produces a total of 12.25 meganewtons, 2,750,000 pounds force, almost triple the thrust of the Saturn V second stage, with this being expected to increase to 15.69 meganewtons, 3,530,000 pounds-force, for Block 2 boosters and later up to 26.48 meganewtons, 5,950,000 pounds-force, with the Block 3 vehicle. During unpowered flight in orbit, control authority is provided by cold gas thrusters fed with residual ullage gas. For such thrusters are located just below the payload bay, and 2 on the oxygen tank. Near the top of the nose cone, there are 2 vents connected to the header tanks. Additional vents were added at the base of the vehicle after Flight 2. The enormous payload bay hosts the nose cone, header tanks, forward flaps, multiple composite overwrapped pressure vessels, COPs, and the PEZ dispenser. The header tanks are mounted at the tip of the payload bay. The liquid oxygen header tank forms the top of the nose cone, with the methane header tank attached directly below it. These tanks terminate in a conical sump, which are attached to the downcomers. Several COPs are mounted in the space around the methane header tank, providing the startup gas for the engines, with 12 additional COPs within the base of the payload bay. The nose cone has substantial internal reinforcement, mainly around the forward flap attachment points and lifting points for the chopsticks. The number of internal stringers was increased between Block 1 and Block 2 vehicles. Additional reinforcements are used to support the PEZ dispenser on ships equipped with one. 4 Starlink antennas are located within the nose cone. The PEZ dispenser is used to deploy Starlink satellites into low Earth orbit. It was first added to S-24, though it was permanently sealed until Flight 3. It consists of the dispenser mechanism and the door. The door opens by folding into the payload bay. The dispenser itself is mounted directly to the forward dome. It has a truss structure for its base, with solid steel used elsewhere. A mobile track is used in the base, enabling the dispenser to push the satellite out of the vehicle. After dispensing a satellite, the next payload is lowered onto the base, and is deployed. The opposite occurs during loading, with the dispenser raising its payloads to receive another satellite. In order to prevent the satellite from floating out of the mechanism during zero-G operations, the dispenser locks the satellites in position using a retention frame. This is lowered alongside the satellites during operation. Starship controls its re-entry with 4 flaps, 2 aft flaps mounted to the sides of the engine bay and locks tank and 2 forward flaps on the payload bay. Substantial reinforcements are present in the nose cone for the support of the forward flaps. According to SpaceX, the flaps replace the need for wings or tailplane, reduce the fuel needed for landing, and allow landing at destinations in the solar system where runways do not exist, for example, Mars. The flaps' hinges are sealed in aero covers because they would otherwise be easily damaged during re-entry. Static wicks are present on the flaps, aiding in the discharge of static electricity. Despite this, damage to the forward flaps was observed on Flights 4, 5, and 6, with near-complete loss occurring on Flight 4. Beginning with Block 2, the design of these forward flaps was significantly changed, moving leeward and becoming thinner and angled. This sets them at an approximately 140-degree angle, compared to the 180-degree angle of the aft flaps and previous version of the forward flaps. This change was made to prevent the static aero from creating a tendency for the ship to pitch up, even when the forward flaps were stowed, and also reduces the heating on the static aero and forward flaps observed on the last 3 flights of the Block 1 ship. Both sets of flaps feature cameras in their hinges. Raptor is a family of rocket engines developed by SpaceX for use in Starship and Super Heavy vehicles. It burns liquid oxygen and methane in an efficient and complex full-flow staged combustion power cycle. The Raptor engine uses methane as fuel rather than kerosene because methane gives higher performance and prevents the buildup of deposits in the engine from coking. Methane can also be produced from carbon dioxide and water using the Sabatier reaction. The engines are designed to be reused many times with little maintenance. Raptor operates with an oxygen-to-methane mixture ratio of about 3.6 to 1, lower than the stoichiometric mixture ratio of 4 to 1 necessary for complete combustion, since operating at higher temperatures would melt the engine. The propellants leave the pre-burners and get injected into the main combustion chamber as hot gases instead of liquid droplets, enabling a higher power density as the propellants mix rapidly via diffusion. The methane and oxygen are at high enough temperatures and pressures that they ignite on contact, eliminating the need for igniters in the main combustion chamber. The engine structure itself is mostly aluminum, copper, and steel. Oxidizer side turbopumps and manifolds subject to corrosive oxygen-rich flames are made of an Inconel-like SX500 superalloy. Some components are 3D printed. A Raptor 2 engine produces 2.3 meganewtons, 520,000 pounds force, at a specific impulse of 327 seconds, 3.21 kilometers per second, at sea level and 350 seconds, 3.4 kilometers per second, in a vacuum. Raptor vacuum, used on the Starship upper stage, is modified with a regeneratively cooled nozzle extension made of brazed steel tubes, increasing its expansion ratio to about 90 and its specific impulse in vacuum to 380 seconds, 3.7 kilometers per second. The main combustion chamber operates at a pressure of 350 bar, 5,100 pound per square inch, exceeding that of any prior operational rocket engine. The Raptor's gimbaling range is 15 degrees, higher than the RS-25's 12.5 degrees and the Merlin's 5 degrees. SpaceX has stated they aim to achieve a per-unit production cost of $250,000 upon starting mass production. On April 4, 2024, Elon Musk provided an update on Starship at Starbase, where two new versions of Starship were announced, Block 2 and Block 3, intended to address the shortcomings of the pre-production prototypes. Block 1 was used after 2020 to 2021 flight tests, beginning with Flight Test 1 at the start of 2023, to Flight Tests 5 and 6, then retired. Block 2 for both stages was used beginning with Flight Test 7 at the start of 2025. Block 2 upper stage vehicles feature a thinner forward flap design, flaps that are positioned more leeward, a 25% increase in propellant capacity, integrated vented interstage, redesigned avionics, 2 raceways, and an increase in thrust. The integrated vehicle is 3.1 meters, 10 feet, taller than the previous Block 1 launch vehicle and was planned to have a payload capacity of at least 100,000 kilograms, 220,000 pounds, to orbit when reused, similar to the original design before the Block 2 rework, but was retired before an orbital flight, with the final estimate of 35,000 kilograms, 77,000 pounds, of payload to orbit. Additionally, Block 2 vehicles were planned to use Raptor 3 engines, removing the need for secondary engine shielding. However, the first Block 2 vehicle, S-33, received upgraded Raptor 2 engines, with an unknown increase in thrust. The Block 2 ship and booster first flew on Flight Test 7. A total of 5 Block 2 vehicles were produced. After Flight Test 11, Block 2 was retired. Block 3 ships have an improved tile design, Raptor 3 engines, as well as hardware for refueling operations low Earth orbit, such as docking ports and a redesigned quick disconnect. The switch to Raptor 3 also enables the removal of most of the aft section's shielding. Block 3 boosters have an integrated vented interstage forward dome, 3 grid fins instead of the prior 4, as well as the use of the grid fins as tower catch points. Like with the ship, the Block 3 boosters use Raptor 3 engines, allowing for the removal of the majority of the booster's engine shielding. Payloads will be integrated into Starship at a separate facility and then rolled out to the launch site. Super Heavy and Starship are then to be stacked onto their launch mount and loaded with fuel via the Ship Quick Disconnect, SQD, Arm and Booster Quick Disconnect, BQD. The SQD and BQD retract, all 33 engines of Super Heavy ignite, and the rocket lifts off. At approximately 159 seconds after launch at an altitude of roughly 64 kilometers, 40 miles. Super Heavy cuts off all but 3 of its center gimbaling rocket engines. Starship then ignites its engines while still attached to the booster, and separates. During hot staging, the booster throttles down its engines. The booster then rotates, before igniting 10 additional engines for a boost back burn, which stops all forward velocity. After the boost back burn, the booster's engines shut off with Super Heavy on a trajectory for a controlled descent to the launch site using its grid fins for minor course corrections. Roughly 6 minutes after launch, shortly before landing, it ignites its inner 13 engines, then shuts off all but the inner 3, to perform a landing burn which slows it sufficiently to be caught by a pair of hydraulic actuating arms attached to the launch tower. The booster landing and catch was successfully demonstrated for the first time on October 13, 2024, with the landing of Booster 12. Meanwhile, the Starship spacecraft continues accelerating to orbital velocity with its 6 Raptor engines. Once in orbit, the spacecraft is planned to be able to be refueled by another Starship tanker variant. Musk has estimated that 8 launches would be needed to refuel a Starship in low Earth orbit completely. NASA has estimated that 16 launches in short succession, due to cryogenic propellant boil-off, would be needed to refuel Starship for one lunar landing partially. To land on bodies without an atmosphere, such as the Moon, Starship will fire its engines to slow down. To land on bodies with an atmosphere, such as the Earth and Mars, Starship first slows by entering the atmosphere using a heat shield. The spacecraft would then perform a belly flop maneuver by diving through the atmosphere at a 60 degrees angle to the ground, controlling its fall using 4 flaps at the front and aft of the spacecraft. Shortly before landing, the Raptor engines fire, using fuel from the header tanks, to perform a landing flip maneuver to return to a vertical orientation, with the Raptor engines gimbaling helping to maneuver the craft. The HLS and depot cannot re-enter the atmosphere, as they lack a thermal protection system, flaps, and other necessary catch hardware. If Starship's second stage lands on a pad, a mobile hydraulic lift will move it to a transporter vehicle. If it lands on a floating platform, it will be transported by a barge to a port and then transported by road. The recovered Starship will either be positioned on the launch mount for another launch or refurbished at a SpaceX facility.